Welcome back, engineers. In our last lesson, we discovered the amazing connection between electricity and magnetism. We saw how moving magnets can create electricity and how electricity can make magnets. Now we're going to put that knowledge to work by learning about motors. Motors are everywhere in fans, cars, toys, computers, and maybe even the device you're watching this on. Take the motor in your kit, connect it directly to your battery block, and let's see what happens. The motor spins. What you've seen here is electricity being turned into motion. But how does electricity actually do that? The answer is, well, magnets. By the end of this video, you will be able to explain how the parts of a motor work together to make a motor work, identify the energy conversions and outputs of a motor component, explain what can be done to make motors more powerful. Let's try something. Take the fan blade and put it on top of your motor, and now let's connect that motor to the battery and watch it spin. If we stack it up this way, the blade should spin clockwise. In the last video, we used the motor and the dual LED to build a generator. When we spun the generator, it created electric current. When spinning one direction, we got one color light, and when we spun the other direction, we got the other color. That told us that current was flowing one direction or the other, depending on the way we turn the motor. If we generate electricity in the opposite direction by spinning the motor the opposite direction, what do you think is going to happen if we apply power in the opposite direction? Let's go ahead and try it and see. We'll disconnect the motor, flip it around, and as we learned in the lesson on polarity, motors are bidirectional, meaning they can work with current flowing both directions. If we connect it in the other direction, the motor is going to spin the other direction. Now it's spinning counterclockwise. We now have a pretty good idea on how to use the motor, but let's dive inside. At the heart of every motor are two main parts: the armature, which is the part that spins. This is a coil of wire that becomes an electromagnet when electricity flows through it. And the stator, that's the still part. This is a magnet too, and it can either be an electromagnet or a permanent magnet. When current flows into the motor, the coil in the armature becomes a magnet. This magnetic field pushes against the stator's field on one side and pulls on the other. This push and pull force makes the armature spin. Motors are all about energy conversion. Our input comes from the battery, that means it's electrical energy. That electrical energy is in the form of a current, which creates a magnetic field. The similar magnetic fields will repel each other, while opposite magnetic fields are attracted to each other. That attraction and repulsion results in a spinning armature. The spinning motion is kinetic rotational energy. There's other forms of energy conversion that you can find with motors as well, such as sound and heat. You might be able to hear the motor spinning, but it's not likely you're going to be able to notice any heat. Unless the component's designed to produce heat, any heat that's generated could damage the component or start a fire. If you notice any pieces getting hot, disconnect them right away. Now that we've learned how motors work and how to use them, let's figure out how we can use them in our creations. Right now, the motor will only spin one speed. While this might be okay if it's the exact speed you happen to want, it's not always going to be right. We're going to need to create circuits that are going to allow us to adjust the speed of the motor. Your challenge is to use all the parts that we've learned about so far and try and create a circuit that allows you to change the speed of the motor. Go ahead and pause the video now and give it a try. How did you do? Were you able to do it? Your circuit probably looked something like this using a variable resistor, either the potentiometer or the photoresistor. Your circuit probably looks pretty similar to the LED circuits we made during our variable resistors lesson. In my example, I used the potentiometer. With our variable resistors, we can slow the motor down. This is a great way for us to be able to control what's going on. But what if we wanted to speed it up? Well, unfortunately, the only way to speed up a DC motor is to increase the voltage. Our max voltage is 3.7 volts from the battery, and as we learned, we can only use those 3.7 volts. If we grab the armature of the motor, we can stop it with our fingers. That's because this motor does not have a lot of power. To increase the amount of power, we need to actually make the magnets stronger. Stronger magnets means stronger push and pull. That stronger push and pull is going to mean that that armature can push more force. As we learned in our last lesson, we can increase the strength of magnets by adding more coils inside the motor. Unfortunately, there's not a way for us to do that without taking the motor apart. When a motor is designed, the number of coils is carefully decided to make sure that the motor fits the need perfectly. Awesome work, engineers. Let's go ahead and review. In this video, we explained the main parts of a motor and how they function together. We identified the types of energy conversions happening within a motor, and we learned how to change the speed and power of a motor. Next time you see a fan spin, a car move, or a robot roll forward, you'll know a motor's at the heart of it, turning electricity into motion. Ready for another challenge? Create a circuit diagram for a fan to cool you off when it's sunny outside. It should automatically turn on and get more powerful as the sun shines down harder on you. First, start by creating that circuit diagram and then build it to see if it works. Explain to a partner, teacher, or family member how it works.